Welcome back to Mathematics Lifeline. In today's video, I want to talk about the quotient rule and how we can prove it mathematically. So, most Calculus 1 students should be able to tell you the quotient rule off the top of their head. It's something that you're expected to memorize, but not always expected to prove. So, we have the derivative of this rational function is this big long term. And that this will always hold provided that f of x and g of x are both differentiable and the g of x is not equal to 0. Right? So as long as those two things hold, the quotient rule holds. Now, when we think about how we can prove the quotient rule, we have to go back to the definition of derivative, right? In any mathematical proof, you need to use definitions that you have. So when we look at the definition of a derivative, remember that's a limit. So we take the limit as h goes to 0, and then we have to do the difference quotient on the inside. So that's that f of x plus h minus f of x all over h. So we're going to do the same thing here. So the first term, we're going to plug in x plus h. So that's going to give me f of x plus h over g of x plus h. And then I have to subtract off my original function. So that's going to be f of x over g of x. And then all of this is divided by h. So this is our definition of derivative. So in order to get the rule out of this, we have to kind of manipulate this limit a little bit. So I think a logical first step, and a lot of times when you actually will do derivatives with the limit definition, we need to combine these fractions in the numerator. So we need to multiply this one in the top and bottom by g of x, and this one in the top and bottom by g of x plus h. Right, that'll give us a common denominator, and then we can directly subtract these fractions. So this is the same thing as the limit as h goes to 0. It'll end up being f of x plus h, g of x, minus f of x, g of x plus h, all over, so our common denominator was g of x plus h, g of x, but we also are dividing by an h. So it's perfectly legal to put an h right here because dividing by h is the same as multiplying by 1 over h. So just to recap that step, what I did was I combined these into one fraction by subtracting them. So I needed to get a common denominator of g of x plus h g of x. And then I was able to combine them into one fraction because once they have the common denominator, I can directly subtract them. So this part is pretty standard. Now, where this gets tricky is to prove this, we actually need to bring in something that isn't already there. So we're going to need to add and subtract the same term from the numerator of this expression. So we're still going to have the limit, but it's going to be f of x plus h, g of x. Now here's where the new part comes in. I'm going to subtract off f of x times g of x. Now it may seem like that's coming from thin air, but it'll make sense why we need to add this term in a second. So let's continue writing our limit out here. So minus f of x, g of x plus h. And now this is where I can justify subtracting here because if I add the same thing, nothing changes, right? Because I could combine these to 0 and we still have the exact same numerator. And then now remember all of this is divided by that h, g of x plus h, g of x. So this is what we've done. So we've subtracted and added the same term. Now the reason that we're going to do that is because now we can split this limit up at this negative sign, and we'll actually get definitions of derivatives that pop out in both of the limits that we make. So let's go ahead and split the limit up. So I get the limit as h goes to 0 of f of x plus h, g of x minus f of x, g of x. And all of this is over that same denominator. So h, g of x plus h, g of x. And then now I'm going to, so that was the first limit. I'm going to now make our second one. So we're going to subtract off, because we're going to use that negative sign. But we're subtracting off this entire term over here, which means this sign will have to change as well, because I'm factoring a negative 1. So I'm still going to have the limit as h goes to 0. Now this term became positive because the negative's right here. So I have f of x, g of x plus h. Now this one will turn into a minus f of x, g of x. And all of that's over the same denominator. Okay. So again, it may not seem completely obvious how this is helping us, but let's think about what the limits depend on, right? This is a limit that is in terms of h. So we're looking at all of the terms that have h in them. Everything else is just going to be some constant in the limit. So when we look at what we have here, we have these g of x terms. So these two right here and this one, but we don't need to worry about that one as much. But these g of x terms can be factored out because they don't depend on h at all. There's no h in the argument of the function. So what I can do is I can actually factor out a g of x. So this is the same thing as g of x times the limit as h goes to 0. Now I'm going to also do one more thing. So I factored a g of x out. So what I have is f of x plus h minus f of x. But I'm going to consider just being over h, right? And this may look familiar. I'll explain it in just a second. And I'll just multiply by 1 over g of x plus h times g of x. Now again, we could absolutely pull this g of x out because it also doesn't depend on h. But then we would just have to reintroduce it at the end because we want it to match this form. So you'll see why not doing that is going to benefit us. So that's our first limit. We're going to do the exact same thing with this one. So I'm going to subtract off. Now let's think about what I can pull out of this. This is still a limit that depends on h. And I have these f of x terms that don't depend on h at all. So I'm perfectly valid to factor those out because they're just constants. So I factor out that f of x. Now I still have the limit as h goes to 0. So I'm going to do the same thing. I'm going to split it up where this is separate, but I'm going to have g of x plus h minus g of x over h, and then I'm going to multiply by the 1 over. So multiply by 1 over g x plus h, g of x. So this is where the beauty of adding in this extra term is, because what we have here and what we have here, that is just the definition of a derivative, right? So this part right here is just f prime of x, and this one is just g prime of x. So now the only other thing is, what is this part of the limit, right? Because technically the limit includes all of this, and the limit includes all of this. So what is this part of the limit? Well, there I can just actually go ahead and plug in as h goes to 0, because then I'll have g of x times g of x, and that's just g of x squared, right? So what I have here after all of this is I'm going to have g of x multiplied by this turned into f prime of x, because that is the definition of derivative. So this is exactly what we did here, just without the rational function part, right? So this is the definition of derivative, and then I'm multiplying that, so I'm multiplying by 1 over, so it's the same thing as dividing. And remember, this went to 0, so I just have g of x times g of x. Well, that's g of x squared. So that's g of x squared. And now this one, the same kind of idea. I have minus f of x, right? That's this part, multiplied by this is g prime of x, because that's the definition of derivative, over g of x squared, right? This is the exact same thing, where if I plug h to 0, I get g of x squared down there. But now you'll notice that these all we can actually just go ahead and directly subtract these, because this g of x can go to the numerator, the f of x can go to the numerator, because it's being multiplied, and they both have this factor of g of x squared in the denominator, so they're valid to subtract. And what we end up getting is g of x, f prime of x, minus f of x, g prime of x, all over g of x squared. And if you notice, that is exactly this form right here. So we've proven the quotient rule, and that's going to be the end of our proof. We got what we needed. Now, again, this is very similar to the product rule, if you've seen my video on that, where we need to add and subtract the same term, just a little bit different, a different term for the quotient rule. But yeah, I think it's pretty cool. I mean, the definition of derivative spits right out of this just by adding that term. So it makes the proof that much easier to follow. But yeah, I hope you enjoyed this video. I hope it made sense. I hope this is something that you're curious about. If you have any questions, let me know. I can try to prove some other derivative rules, because there are some cool ones that we can prove. And yeah, if you don't have any questions, then I will see you in the next video. Thanks for watching.